Once you understand reaction mechanisms, it becomes a lot easier to understand catalysts at a deeper level. So, a catalyst is just a substance that increases the rate of a reaction without actually being consumed in the reaction. So we're going to look at how catalysts are involved in the mechanism of a reaction, because really what they do is they change the mechanism. They're responsible for lowering the activation energy of a reaction by providing a different path or a different mechanism for that reaction. And remember, when you lower the activation energy, a lower activation energy will result in a faster reaction. There's two types of catalysts. A homogeneous catalyst is present in the same phase, and a heterogeneous catalyst exists in a different phase, so solid, liquid, or gas. Homogeneous will be a solid in a solid or a liquid in a liquid. Enzymes are catalysts that increase the rate of biological reactions. Our bodies are filled with enzymes that catalyze or speed up our reactions. Let's take a look at an environmental catalyst. The upper atmosphere is home to the ozone layer, which is destroyed by CFCs or chlorofluorocarbons. Chlorine reacts with ozone in the following mechanism. So first we have chlorine reacting with ozone to create this chlorine oxygen compound and oxygen. Then the chlorine oxygen compound reacts with an oxygen atom to create a chlorine atom and oxygen. So a chlorine atom is used and then it's released. So if we add up this reaction and look at some of the parts that are on both sides, we can identify what those parts on both sides are doing and how they relate to the overall reaction. So we have chlorine at the beginning and chlorine at the end. They will cancel out, so you won't find a catalyst in the actual chemical equation, but it's something that's required, it's something that's used and then created. This is our catalyst. If it's something that's used and then created at the end, you will not find the catalyst in the balanced chemical equation because it cancels out. Another thing you will see here is the chlorine oxygen compound that is created in step 1 and used immediately in step 2. Remember, this is called a reaction intermediate. So it's an intermediate is just a substance that's created and then used right away. We will not find a reaction intermediate in the overall balanced chemical equation. So we don't find catalysts and we don't find intermediates in the balanced chemical equation. So what is the equation, the overall equation for this process? Well, overall, we have not canceled out the chlorine or the ozone and the oxygen atom. And that creates, the ozone and the oxygen atom create two molecules of oxygen. So the catalyst is the chlorine atom, and the intermediate is the chlorine oxygen compound. What makes this catalyst so dangerous is that once it catalyzes that ozone reaction, it can be used again to catalyze another reaction and another reaction because it never gets used up. Let's take a look at a reaction pathway, or the reaction pathway for this reaction. We have ozone plus an oxygen atom. Now, you're going to see two hills here. One of the hills is for the uncatalyzed reaction. That's our blue hill. Now you'll see in this uncatalyzed reaction, you'll see a very, very high activation energy. There's one step to this reaction. There's one activated complex in this reaction. So this requires the input of a lot of energy. This is our uncatalyzed reaction. This reaction would happen very slowly because it would take a long time for enough particles to get enough energy to actually create a reaction. However, there is a reaction mechanism that involves a catalyst. Now this mechanism is a two-step reaction. So you're going to see two little hills there in the red. And those two little hills represent activated complexes for individual steps. So this red line is the catalyzed reaction. So if we have a catalyst, if we have that chlorine atom in there, then we have the catalyzed reaction. And there are two little separate, much smaller activation energies. One for step 1, and then we have our reaction intermediate where it goes down. And then another activation energy for step 2, and then we get our products. So this is our our first activated complex, or activated complex number 1. Remember, that's a higher energy particle. And then we have our intermediate, which is a lower energy, much more stable molecule. This is the molecule that gets created and then used. It gets created in step 1, so this is the CLO. It gets created in step 1 and used instantly in step 2. So it's a lower energy molecule. This is not part of the balance equation. And then we have step 2. We have an activated complex for step 2 of the reaction. So we'll call this activated complex 2. And then we get our energy out. So then we have that overall exothermic reaction for this. So overall, we get the same amount of energy out, but when we have a catalyzed reaction, we have a much lower activation energy, which causes this reaction to happen a lot quicker than the blue reaction, which was our uncatalyzed reaction. Remember, the lower the activation energy, the faster the reaction. So I'll write that out here so you don't forget. The lower the activation energy, the faster the chemical reaction. So if a catalyst can lower that activation energy, that will speed up the chemical reaction.